If we were asked to provide a tour of our data center and our network, would it be the same tour every time? So for example, in an office, we could walk in and say, okay, here's some computers, we'll start there. And we have several different types of servers that connect to our network. And when they have physical connections to a network, they're usually connecting over to a switch. We could also have some voice over IP devices that are connected. Now, a computer could be running a soft phone, an application on their computer that behaves as a phone, or they could have a separate physical IP phone, which is providing that functionality. And one cool technique is that instead of having two cables come out from the switch, they have one cable that goes to the phone, then another cable that goes from the phone to the computer. And the trick they can use here is they can do trunking and have a separate logical network for the phone traffic, the voice over IP, and a different logical network that's being used for the packets that are coming to and from the computer. So the actual endpoint for a voice over IP device depends on how it's being implemented. Those switches are normally going to be on the same floor in the building where those users are. And let's use this building as an example. And this building has 3 floors. We have the first floor there, and then the second floor, and the third floor. And on the third floor, we have a user like Bob with his computer, and that computer is connected over to a little jack. And there's a patch cable going between that jack and his computing device. And then from the jack, there's a horizontal run that usually goes in some area that we can't see, very likely a ceiling area, or possibly just beneath the floor. And that goes over to the wiring closet on that floor. That's also sometimes referred to as an IDF, an intermediate distribution frame, a term from the telephony days, when most of our cabling was basically telephone connections. And that horizontal run connects to a layer 2 switch in the wiring closet. And the same thing for Lois on the second floor. And then to connect everything together, we have some vertical runs that go between the floors. And it can connect the access layer switches on these floors to a bigger switch down in the data center here on the first floor. And if we're going between 2 different connector types or 2 different types of media, if we don't have the interface that directly supports that media interface or that media type, we may need to implement a media converter so we can make a connection if we don't have a native adapter or interface that supports the media type. So in the wiring closets, we're going to have a lot of layer 2 functionality. And as far as routing goes, layer 3 forwarding of packets, that's very likely going to be done down here, where we'll have higher end gear and very likely multi-layer switches that can do layer 2 forwarding and layer 3 routing in the same gear. Another common device that we're going to have in most networks is a firewall. And a firewall does layer 3 packet forwarding, very similar to a router, but firewalls have an attitude, and that attitude is something like this: no, regarding traffic that's trying to come into the network. Now, at the same time as saying no to connections that are initiated from the outside, the firewall is also stateful in nature. So that if Bob, over here on computer 2, is making a request out to an internet resource, on the way out, the firewall is remembering that session, the state of that session. And then if the server replies back in response to Bob's request, the firewall will take a look at stateful session tables and say, well, you know what? This is a reply coming back to Bob based on something he asked for. I will go ahead and let that return traffic come back in. Another common phenomenon that's happened in the last decade or two is wireless networking. So here we have a wireless device. It could be a computer or a mobile device. And the way it connects to the network is through a wireless access point shown right here. So the wireless access point is connected to the switch, and then it's communicating with the wireless devices via radio frequency back and forth. Now, a single access point running all by itself is commonly referred to as an autonomous access point. All by myself. And in a situation like that, hopefully that one access point can cover the entire area that needs to be covered. And if we have some areas that can't quite be covered by that single access point, we can get a wireless range extender, and that physical device can help extend the range beyond what the single access point can do on its own. However, in most corporations, they're not just going to have one access point. They're going to have several access points or hundreds of access points. And in those scenarios, they implement a controller that communicates with the access points. So the administrator talks to the controller, and then the controller talks to the access points. And there are some devices that we're not going to see too commonly anymore, including hubs, a layer 1 device, just a multi-port repeater. They've been out of favor ever since we got switches many decades ago. Another thing that's slowly moving away are the asynchronous modems. Modem stands for modulator demodulator. In the old days, if we had a user like Bob on the internet who needed to access corporate resources, he would get his modem, his modulator demodulator. It was connected to a serial port, and then he'd also connect it to a phone line, and then use the public switch telephone network, dial a number, connect to a modem, at the corporate site to some server here, which would then give him access. And because today we have so many much better options most of the time, we don't see a lot of asynchronous public switch telephone modems being used anymore. However, what is popular now are things like cable modems to get access to the internet from a service provider who's providing cable services. And one other item that we're not going to see too often is a bridge. Now, a bridge is a layer 2 switching device. So before we had switches, we had a bridge that would do that layer 2 forwarding, but it didn't have a whole bunch of ports. So we can think of a bridge as the great-great-grandfather of our current modern-day Ethernet switch. One of the things I've always loved about networks is that they're like Tinker Toys. We get to put all these little pieces together, and it's a wonderful thing. And so in this, let's take a look at this network right here, and let's go through some of the configuration we'd want to do so it's functional. So let's chat about some things we'd want to configure. Number one, if we're going to be using VLANs other than the default VLAN 1, we'd want to assign these switch ports to the appropriate VLANs. And that way we're carving out our layer 2 networks, and then we'll assign IP addresses. Our clients need IP addresses, the router interfaces need IP addresses, the firewall interfaces need IP addresses, and even our switch, even though it's a layer 2 device, if we want to manage it remotely, we can have a logical interface, just for management purposes on the switches as well, that it's going to need an IP address. And once we have our IP addresses set up, normally it's one IP network per VLAN. In order to move packets between network A and network B, between two different IP networks, that's the job of a router. And the router needs to learn how to forward traffic. So we'd also want to configure either static routes in a very small network or use a dynamic routing protocol. And allow the routers and routing devices to talk to each other to share route information so that the learning can be dynamic regarding how to reach layer 3 networks, which way to forward a packet to get to a network. On our firewalls, in addition to using stateful firewalls, it's very likely we're going to want to have some kind of access controls and filters in place to further restrict the types of traffic that are allowed to be sent through the firewall. And if we have lots of clients, it's a pain in the bazooski to do manual IP address assignment for all of our clients. So it's likely we're going to use a DHCP server and train our clients to be DHCP clients. So that way we don't have to manually statically configure each and every client that needs an IP address on our network. And then last but not least, we're going to need somewhere in our network address translation if we're using a private RFC 1918 address internally and we want our clients to be able to send packets out over the public internet. So that network address translation can be done either on our router or we could do it on our firewall, but it needs to be done somewhere because the service providers on the internet will not route RFC 1918 private addresses. So here's another view of our network topology that includes some additional information, including interfaces on the routers and switches, as well as some IP addresses in our topology. And the reason I want to introduce you to the details for this topology is because this is the lab environment that we're going to be using over the next several nuggets as we go through together the configuration of many aspects of this lab topology. So PC1 is connected to switch 1 on port 00 of the switch, and router 1 is connected to port 0/1 on the switch. So if we want router 1 and this PC both to be in VLAN 100, we need to configure both of those ports, port 00 and 01, to be in VLAN 100. On a Cisco switch, if we issue the command show VLAN brief, it can show us the VLANs and the ports that are assigned. Here we have VLAN 100, and currently we have port gig 00 and 01, both assigned to VLAN 100. That's perfect. We'd also want to assign appropriate IP addresses to each of our interfaces. So the routers would need IP addresses on their respective interfaces, and so would the firewall, and of course the PC as well. So if we take a peek at router 3 on a fully configured network, we can verify that the 1/0 interface has an IP address on the 10.23 network, and that interface 2/0 has an IP address on the 67.83.45.0/28 network. So here on a Cisco router, we can do a command like show IP interface brief, just to verify what the IP address assignments are and that the interfaces are up. That looks good on router 3. And there's other commands we can issue as well, including show IP interface for gig 2/0, which will also reveal the IP address that's assigned on that interface. And if we just do a show interface for gig 2/0 without specifying IP, it'll give us that same information, as well as some other details about that interface, including the duplex, whether it's half duplex or full duplex. And to make it easier to hand out IP addresses, we could configure DHCP services either on a traditional server, and another option is we could actually use the DHCP service on a Cisco router that supports that function to dynamically hand out IP addresses to PCs on local subnets. So here on router 1, if we do the command show IP DHCP pool, it'll show us information, if there is one, regarding a DHCP pool or scope set up on that router. We have other commands such as show IP DHCP binding to show us exactly which IP addresses are associated with which MAC addresses. And we have additional commands such as show IP DHCP conflict, which is going to show us any conflicts where the DHCP server is going to hand out an IP address, but it checked first and the IP address was already in use, and those are going to show up as conflicts on the DHCP server. And for our network address translation, it's very likely in this topology, we do it right here on router 3. And we can indicate that traffic coming from the 10.1.0 network should be translated before it's sent out over here to the internet. So here on router 3, if we use the command show IP NAT translations, it'll show us all the translations that are currently in place on this NAT device. And if we use the command show IP NAT statistics, here it indicates that it's using access list 1 to identify who can be translated, which equates to the 10.1.0 network. It's also identifying the pool called our pool, also sometimes called a scope, that has a range from .11 to .14. And those would be globally routable addresses assigned to us by the ISP. In this hands-on lab, you and I get the opportunity to configure a couple of switch ports to be associated with VLAN 100. Associated with this nugget, there's a link where you can launch the hands-on lab, and I would love it for you to get the hands-on practice in configuring the switch ports. So we'll be working on switch 1. We're going to be focusing on ports gig 00 and 01. We're going to put both of those ports, those two ports, into VLAN 100. And to do that on this Cisco Catalyst switch, here's the syntax. Configure space terminal will take us into configuration mode. And then we're going to further go into interface configuration mode for the first interface, which is gig 0/0. We're going to use the command switch port mode access, which says be an access port as opposed to be a trunk port. And then we're going to specify which VLAN it should be associated with. So the syntax is switch port access VLAN 100, and that's done for gig 00. And then we'd repeat that process for interface gig 0/1 by going into interface configuration mode for gig 0/1 and issuing the exact same two commands, and then we'll type an end to exit configuration mode. Now, how do we verify our work, and is that important? I'd say yes, very, very important. And to verify that both these ports are associated with VLAN 100, we can use the command show space VLAN space brief, and then press enter. And that can confirm for us that those two ports are indeed associated with VLAN 100. And for this lab, everything else is already configured. So once we have these two ports in the correct VLAN, we should be able to ping from PC1 out to a resource out here. So in this lab environment, I've got a resource at this IP address. Makes it real easy, 4.4.4.4. So PC1 should be able to ping that IP address, and it should go all the way through the network. And we can verify that further by doing a trace. On this virtual machine, there's a command called trace. If we do a trace to that same IP address, it'll show us each of the hops in the path. And so we should see the first hop, the first router being R1 at this interface, and then the firewall at this interface, and then router 3 at this interface. And then in the lab topology, I just have a simple router right here that's playing the role of the internet. And behind the scenes, that's a little guy called Mr. Router 4 who has this IP address 4.4.4.4 that he can respond to. And so now we're at a fork in the road. We have a couple of options. Number one is you could go ahead and do this lab if you're logged on from a computer. And then after you finish the lab, you could resume the video and then verify the results that you had from the hands-on with what I'm demonstrating in the video. Or if you're on a mobile device or you can't get to the lab right now, go ahead and watch the rest of the video to reinforce the concepts. And then when you have a chance, take a moment or two and do the hands-on lab practice to reinforce the concepts as well. So here on switch 1, let's do a quick command of show VLAN brief just to verify our starting point. So we're starting with gig 00 and 01 being in VLAN 1. We want them in VLAN 100. So we'll go into configuration mode with the configure space terminal, or you can do a conf space T for short. Then we'll go into interface gig 0/0. We use the command switch port mode access to tell it we want to be an access port. And then the command switch port access VLAN and VLAN 100. Super. And then we'll go over to interface gig 0/1. I'm using the up arrow key to save a little bit of typing there. And now we're in interface config for 0/1. And we'll do those same two commands again. Switch port mode access. And I'm just using the up arrow key to bring those commands back from history. And switch port access VLAN 100. We'll type an end to exit out of configuration mode. And then we can issue the command show VLAN brief and press enter just to verify that those two access ports are now associated with VLAN 100, which they are. Now let me show you something else that's pretty cool. If we do a show spanning tree for VLAN 100, and this is this is important, and I'm glad we caught it when we did. Check this out. Spanning tree is always on the lookout for layer 2 loops. And as part of that, when ports are assigned to a VLAN, it wants to make sure that that's not a parallel path for that specific layer 2 VLAN. And so as a result, it goes through a listening and a learning state before it goes to forwarding. So gig 00 had listened and learned long enough, and now it's in a forwarding state. And when we caught it just now, gig 0/1 was going through the learning state. And because it's been more than 15 seconds, if we hit the up arrow key and press enter again, now we can see that both ports are in a forwarding state, which is great. So if we had just changed the port assignments and then tried to ping immediately after without waiting a few seconds, the ping wouldn't work until the switch gave its 2 thumbs way up and allowed traffic to flow for VLAN 100 through these ports. So now that it's forwarding, now let's go over to PC1 and test our ping. Also, if you need to see the topology again, there's a couple of ways of doing that. If you want to watch the video on a mobile device and do the lab on a computer, that's handy. Also, if we minimize the terminal window here for a moment, I also included the topology right here, so it's very easy to get to when you're working on the lab. All right, we'll bring back the terminal window, and let's test our ping here from PC1. So we'll ping out to 4.4.4.4, press enter. And that seems to be working. Sometimes there's an initial packet lost with an ARP request somewhere in the network path. So if you lose the first packet out of 5 occasionally, it's very likely due to an ARP request somewhere in the path. And if we want to verify the path, we can also do a trace command. And if we type in trace space and press enter without any options, here it's showing us that by default the trace command followed by an IP address is going to use UDP at the transport layer. If we want to use another protocol like TCP or ICMP, if we want to use a different protocol, we can use the -P flag and specify protocol number 1 or protocol number 6 instead of the default protocol number 17, which is UDP. So let's go ahead and do our trace with trace space and then 4.4.4.4, press enter. And that is a home run, with our first hop being router 1, our second hop being the firewall, our third hop being R3, and then our last hop is right here. This guy is playing the role of our service provider router. And that's where the trace ended, because this IP address is actually owned by router 4. So this is showing us our full path through our lab environment. And again, I would invite you to practice this hands-on to reinforce the concepts. A big part of any functioning IP network is to have correct IP addresses on all the layer 3 interfaces. And those include routers. So we're going to use our lab topology once again for this lab, and everything is configured for connectivity across this network except for the IP addresses right here on router 3. So if you're using a computer to log on to the CB2 Nuggets website, I would encourage you to click the link for this lab and get the hands-on practice in configuring IP addresses on router interfaces. So on router 3, we're going to go into configuration mode. And once we're in global configuration mode, we'll go further into interface configuration mode for Gigabit Ethernet 1/0. That's this guy right here. And we'll use the no shutdown command. Now Cisco routers, by default, most of their interfaces are shut down by default. So if you want them to work, you have to bring them up. And the way you do that is the same way I taught my Cisco dog to stand. And that was the command no sit. Very similar concept here. No shutdown brings the interface up. And then we'll apply an IP address, and the IP address will be IP address space 10.23.0.3 with a 24-bit mask here. And then as we go to interface gig 2/0 over here on the right hand side and use the command IP address 6783.45.3 with a 28-bit mask. And that's the dotted decimal notation for a 28-bit mask. So we'll do our configuration here on router 3, and everything else in the network is already configured. So if it is successful from PC1, we should be able to do a ping out to 4.4.4.4. And we should also be able to do a trace out to that same IP address and see each of our hops in the path to that final destination, which is a little router at the edge that's simulating the internet for the benefit of our virtual lab. So let's go over to router 3. So here on router 3, let's start off by doing a show IP interface brief, just to verify where we're at to start with. So on this router in our lab environment, it shows that these interfaces are currently up, which means we don't have to go through the step of doing a no shutdown command on those interfaces. If these were shown as administratively down, we definitely want to do the no shutdown command on both interfaces to make sure the interfaces have a possibility of working. So because they're already up, we'll focus our energy on configuring the IPv4 addresses. So we'll go into global configuration mode with the command config space t, which is short for configure space terminal. And then we'll go further into interface configuration mode for interface gigabit 1/0 and press enter. And here in interface configuration mode, we'll give it the IP address of 10.23.0.3 with a 24-bit mask. And then we'll go into interface gig 2/0. That's the interface facing our service provider over on the right-hand side. And we'll give it the IP address of 67.83.45.3 space, and then the 28-bit mask, which is 255.255.255 dot. And for that last octet, we're going to take 4 bits, which is 240, and press enter. So now we'll type in end to exit all the way out of configuration mode. And let's do a show IP interface brief. And that looks pretty good. We can take a further look at those interfaces with a command like show IP interface for gig, and then pick the interface gig 2/0 and press enter. And on a Cisco device, it's going to give you one page at a time. When it says more, we can press enter to proceed one more line at a time, or hit space to do one whole page at a time, or we can press any other key on the keyboard and that simply stops the output. So I happen to tap Q just because it reminds me quit, as in quit showing me the output. So here it's showing us the IP address of 67.83.45.3 with a 28-bit mask. That's great. And another way we could see that IP address information would be a show interface without the IPs. Just show interface gig 2/0 and press enter. And I'll hit Q once again. And with the command show interface gig 2/0 without the IP, it still shows us the IP address right here. And it's also showing us the speed and duplex. So this is a 1 gigabit interface running at full duplex. So when working with layer 2 switches, every port on the switch has a send and receive pair of wires that it uses. And as a result, there will never be a collision. So when we're connected to a switch where we won't ever have a collision, because every port effectively is its own collision domain, with a full lane of traffic for sending and receiving, we actually turn off or disable CSMA-CD, carrier sensing multiple access with collision detection, because there aren't going to be any collisions if we're all connected to switch ports. So let's test our end-to-end connectivity. We'll go back to PC1, and on PC1, let's go ahead and do a trace over to 4.4.4.4. And that looks good. And if we want to do a ping, that would work as well. And we could verify that real quick by just doing a ping out to 4.4.4.4. And sure enough, we have full connectivity from our PC all the way out to the internet service provider router in our lab topology. So I encourage you to take some time and do the hands-on practice to help reinforce what you are learning in these nuggets. And as you continue to practice, it becomes easier and easier, and your skills get better and better and better. A router knows exactly how to reach directly connected networks because it's directly connected. But for everything else, it's going to learn it via a static route or through a dynamic routing protocol. In this hands-on lab, we're going to configure both. So we'll use this topology. It hasn't changed since our other labs. And everything is configured for full connectivity except for router 1 is not configured with any static routes, nor does it have any dynamic routing protocols that are running. So what we'll do on R1 is we'll go into configuration mode on this Cisco router by typing in config space T or configure space terminal. Either way will get us there. And then we're going to add a static route. And this static route is for a default route, which effectively tells the router, hey, listen, buddy, if you don't have a more detailed route or better information on how to forward a packet, go ahead and use this Obi-Wan Kenobi route. Help us, Obi-Wan. You're our only hope. And the syntax is IP route, quad zeros, followed by quad zeros. That represents the default route. And then we're specifying the next hop. And that next hop is our good buddy, the firewall, at 10.12.0.9. So it's like hot potato. If router 1 gets a packet, doesn't know exactly detailed information on how to forward it, he's just going to forward that packet over to the firewall, and now it's the firewall's problem to forward it any further in the network. So that'll configure a static default route for R1. However, what's also at play in this network is that we're also running RIP version 2. And that's already configured on the firewall and on router 3. So if R1 wants to dynamically learn more specific routes, it can also join this RIP routing party. And here's the syntax to enable RIP on router 1. So we're in configuration mode already. We'll type in router space RIP. That puts us into router configuration. And then we're going to specify the version. Version 2 supports variable length subnet masks, which is handy in most networks today. And then this statement, the network statement, specifies which interfaces are going to be participating, sending updates and listening for updates on this router. So with the network statement of 10, this is a Class A network, because the first octet is within the range of 1 through 127, and with 127 being a loopback address. But 10 is definitely in that range, and because it's a Class A, The router then says, okay, great. The first octet by default should be the network. And as a result, any interfaces that have IP addresses that begin with 10, like this guy, which both begin with the number 10 in the first octet, they are going to be participating. Now, we could also, if we wanted to say every single possible interface, another option for the network statement is network space, and then 4 zeros separated by 3 periods. And with a statement like this, it tells the router, I don't care what IP addresses on my interfaces. I want them all. If they're running IPv4, I want them all to participate in RIP. So with the network 10.000, we're limiting the RIP routing process to just interfaces that have IP addresses that begin with 10, which in our case will be perfectly fine. We're also going to specify the command of no auto summary because it likes to summarize by default. So we're going to turn that feature off. Then after a few seconds, R1 is going to learn some information from his good buddy the firewall. He's also going to share some information with the firewall. And when all the routers running the routing process know how to reach all the networks within their control, that's referred to as convergence, or the network has converged, or finally figured out how to reach all the networks in our routing domain. And then we'll type in end to get out of configuration mode, and then we'll verify our work. So here on router 1, let's do a show IP route just to see what we have to begin with. So if we look up here at the codes, L is local and C is connected. And at the moment, R1 is like Sergeant Schultz from Hogan's Heroes. I know nothing except for directly connected in local networks. So let's change that. Let's go into configuration mode by typing in configure space terminal or the shortcut conf space T. And now that we're in global configuration mode, we'll create a static route, IP route, and we're going to put in the default route, which is 0.0.0.0 space 0.0.0.0 space, and then the next hop for our default route, which is going to be the firewall at 10.12.0.9, and then we'll press enter. Next, in order for R1 to be able to play the game of RIP with the firewall and dynamically learn routes and share routes, we need to configure the RIP routing process on R1. So we're already in configuration mode, so what we'll do is we'll type in router space RIP and press enter. We'll specify the version that we want to run, which is version 2. We'll add our network statement, which is the 10.0.0.0, press enter, and then we'll also specify the no auto summary command, press enter, and we've now configured the RIP routing process on this router. So we'll type in end to go all the way out of configuration mode, and now we'll wait just a few moments for RIP to converge, and then we'll do a show IP route, press enter, and now we have a few additional routes that we've learned on this router. So with this show IP route command, any RIP learned routes will have an R in front of them. So there's one and there's one. And because we're learning all this information from the firewall, if we look at the next hop for all those RIP learned routes, they are all pointing to the firewall because he's the guy who advertised those routes to us. Now, in addition to the dynamically learned RIP routes, we also have up here our static route that we added manually, which is also using the next hop of the firewall of 10.12.0.9. So as a test, let's go over to PC1, and we should be able to reach a resource that's on the other side of the network. So let's go ahead and do a trace here on PC1 to 4.4.4.4, and that's successful. And because the trace worked, it's also very likely that a ping would work as well. So let's go ahead and verify that with a ping out to 4.4.4.4, press enter, and sure enough, those pings are working fine too. And that's because PC1 is using R1 as its default gateway. And when that packet is received at R1, R1 has routing information, including a default route, to continue forwarding that packet in the direction of the destination network. So a good approach to reinforce what you are learning is to do the hands-on lab and have some fun with it as you build your skills in working with networks. Give me a D, give me an H, give me a C, give me a P. What do you get? An IP address. In this, we're going to walk through the configuration of a DHCP service on a DHCP server, and then we'll verify it by setting up a DHCP client. Now, it's been scientifically proven that if we want to have DHCP services, we need a couple of players. We need a server who's offering IP addresses and a client who is requesting and using IP addresses. So for this lab, let's go ahead and configure the DHCP service on the Cisco router itself. And we'll use PC1 in our lab environment as a DHCP client, where the client does the discover, the server does the offer of an IP address, the client does a request to take it, and the server sends the final acknowledgement. And on a Cisco router, here's how we would configure a router to act as a DHCP server. We'd enter configuration mode with configure space terminal or config T, and then we'd use the command IP space DHCP space pool space, and then the name of the pool that we want to create. In our lab, let's go ahead and create a pool called scope-1. And when we press enter, it's going to take us into configuration mode for that pool. And then we can specify the details. including what network address space do you want to hand out IP addresses from. And this network down here is the 10.1.0 network. So we'll hand out IP addresses from that network address space by using the command network space 10.1.00 with a 3-octet mask to indicate that this is the network that we want to pull from. So by default, it would use .1 all the way through .254. However, that IP address of .1 is already in use. So we also might want to set up some exclusions, which we'll do here in a moment with this command right here. So that's coming up shortly. While we're still here in the pool configuration mode for scope 1, we could also hand out some options, including the default gateway that we want PCs to use. The syntax on the Cisco router is default-router, and then the IP address that we want the PCs to use as a default gateway. And we can also hand out information such as a DNS server. If we hand out that information as an option, then the client will know who to go to when it needs to do DNS queries. And then we'll go ahead and we'll configure the exclusion range. Now, there's a couple of options. We could type exit right here, and that would remove us from the pool configuration mode back to global config, or we could just type in this command and that would automatically step us back to global config, so that command would work. Either way will work great. So the syntax for the exclusion is IP DHCP excluded-address space, and then the first in the IP address range that we want to exclude, and then the last. So what this says to the router is, I won't be handing out the .1 through .20, and so it's very likely that the first DHCP client will get the IP address of .21. And then we can type in end to take ourselves completely out of configuration mode, and then we can test it by going to PC1, telling it to use DHCP to get an IP address, and then with that DHCP address assigned to the client, we'll verify network connectivity. So here on router 1, we'll go into configuration mode. And then from configuration mode, we'll create the DHCP pool called scope-1. And now we're in pool configuration mode for that specific pool. And we'll put our network statement in of the 10.1.0 network with a 3-octet mask that's on. Then we'll specify the IP address that clients should use for a default gateway. In this case, it's going to be R1's address because he's the only router on that subnet. Also, as part of our options, we'll hand out the IP address of a DNS server that the client can use as well for name resolution. And then just for clarity, I'm going to type in exit to take us out of the pool configuration and back to global configuration mode. And from here, let's go ahead and do our exclusion. So we'll use the command IP DHCP excluded-address, and then the first IP address in the range of 10.1.0.1 with a space, followed by the last IP address in the range that we want to exclude, which is 10.1.0.20. And then we'll type in end, and we now have it configured. We can verify the pool with the show IP DHCP pool, press enter. So here's our range of .1 through .254, but we have 20 of those which are excluded, which is the first 20. And currently, we have 0 leases, and that's because we have 0 clients who are using DHCP. Let's fix that right now by heading over to PC number 1. So here at PC 1, if we do a show IP, currently it's using the IP address of 10.1.0.11, and on this virtual PC, in order to cause it to be a DHCP client, we're going to use the command IP space DHCP and press enter, just like that. And then it's going to go through the discover, offer, request, and acknowledgement process, assuming it works, and it appears that it did. So that's what these letters represent. So I had a D, and then it looks like it didn't get a response, so it followed up with another D for a discover, and then it got an offer from the server, then there was a request from the client, and a final acknowledgement from the server, and the IP address it got was 10.1.0.21. It also received the option of a default gateway or default router to use at 10.1.0.1. And if we do the command show IP on this virtual machine, it has additional information here, including who the DHCP server was that gave us that IP address, and also details about the lease. So now let's do a test. Let's do a trace to 4.4.4.4, which is an IP address on the far right on our simulated internet here in the lab environment. We'll press enter, and that verifies connectivity as well as the path that we're taking to get to that destination, which includes our default gateway, the firewall, router 3, and then our router in the cloud at 45.4. So if you haven't already, I invite you to practice hands-on in the lab environment that we've provided to help reinforce and build your skills in working with network devices and their configuration. If you and I, when dealing with our bank, had to go physically to the bank every single time we did any type of a transaction, that wouldn't be that convenient. And we have that same kind of consideration when we're managing a switch. Think about it. If every time we manage this switch, we had to physically go to the wiring closet where that switch is and physically plug in a console cable to the console port so we could make configuration changes on it, that doesn't scale very well, especially if we have lots and lots of switches. So we need a way that we can associate an IP address with a layer 2 switch for the purpose of management. So we can remotely connect to the switch, and then over that connection to that IP address of the switch, we can then do the management. And in a Cisco environment, the way that we assign an IP address for management to a switch is by creating this beautiful little construct referred to as a VLAN interface. So at the moment on this switch, it's got 2 access ports that are in this topology. They're both associated with VLAN 100. Gig 00 goes to PC1, gig 01 goes to router 1. And if we wanted to create a reachable IP address for this switch that's associated with VLAN 100, here's how we would do it. We'd go into configuration mode on the switch, and we'd use the command interface space VLAN space 100. And when we press enter, poof, that magically creates this logical interface called interface VLAN 100. So we know that a VLAN is a layer 2 broadcast domain. That has not changed. What we're doing now is we are creating a logical interface on this switch called interface VLAN 100 so that we can reach this switch over that VLAN and connect to an IP address associated with the switch. So once we press enter, we'd go ahead and use the no shutdown command to go ahead and bring that logical interface up so it's available to be used, and then we'd assign it an IP address. So if this is the 10.1.0 network, we would want to use an IP address somewhere in that IP address range. So for this demonstration and for this lab, let's go ahead and use 10.1.0.5 as the IP address we're going to associate with this interface VLAN 100 on switch 1. And we have one other little challenge that I'd like to address right now with you, and that is this. What if we are sitting over here and we're on VLAN 20 off of a different switch? So this is our management PC here. And let's imagine our IP address is 10.2.1.5. If we establish a connection over to the management IP address of 10.1.0.5 on switch 1, when switch 1 tries to respond to us, this layer 2 switch by default doesn't know how to route. It doesn't know how to reach anything except for the 10.1.0 network in VLAN 100. So we'd also, very similar to what we do on a PC, we'd also want to give this switch the concept or the idea of a default gateway. How to forward packets to a router who could forward those packets to a remote network. And so to do that, in global configuration mode, we'd use the command IP space default-gateway on this Cisco switch, and then the IP address of the default gateway that we want the switch to use. And that way, when this PC here at this IP address makes a connection, the switch 1 can respond back using its default gateway, who can then route the packet in the direction of our management station. So if you're at a computer, I'd invite you to log on and do this hands-on practice with me. And when it's configured, what we should be able to do is we should be able to, from switch 1, do a ping out to another network. And so over here we have the 4.4.4 address out here in our simulated internet cloud. So switch 1 should be able to ping out to 4444 and get a reply back. And if that ping is successful, that's going to help us verify that we've got the IP address on this logical interface configured, and we've also got a correct default gateway that the switch can use to forward packets beyond the local network it's directly connected to. So let's do a couple things real quick just to verify our current configuration. Let's do a show VLAN brief. We can verify that we have a couple of access ports associated with VLAN 100. That's great. And let's also issue the command show IP interface brief just to verify if there's any VLAN interfaces already there that are currently configured with any IP addresses. So by default, we have a VLAN 1 interface, but it does not have an IP address. And a lot of companies do use VLAN 1 to manage their switches, but in our topology, we have no other devices in VLAN 1. So we're going to create a logical VLAN 100 interface and assign it the IP address of 10.1.0.5. So to do that, we'll go into configuration mode with configure space terminal or conft. We'll create the new VLAN interface called interface VLAN 100 by typing in exactly that. It appears that this new logical VLAN 100 interface is down, so we'll bring it up with the no shutdown command. And next we'll assign it an IP address. And this is the same syntax we'd use on a Cisco router on one of its layer 3 interfaces. And that syntax is IP space address, then the IP address that we want to use, followed by the appropriate mask for that network segment. So now we have a VLAN 100 interface associated with VLAN 100 with the IP address of 10.1.0.5 that we can now use for managing this switch if we're coming from the 10.1.0 network, because the switch at the moment doesn't know how to forward packets anywhere except for that directly connected network. So let's type in exit to go back to global configuration mode, and let's add a default gateway with the command IP space default gateway space and then the IP address of the router that can forward packets off of this local network on behalf of the switch. and that's going to be the default gateway of R1 at 10.1.0.1, and we'll press enter. Then we'll type in end to go out of global configuration mode, and let's do a show IP route. And at the moment, this switch is just configured as a layer 2 switch. Here it shows the default gateway is 10.1.0.1. That's great. And if we issue the command show IP interface brief, we now have this new VLAN 100 interface with an IP address of 10.1.0.5 associated with it. So we should be able to ping out to, let's do a ping to 4.4.4.4 and press enter. And so that first period represents a timeout. The first ping didn't make it for whatever reason, and the last 4 did. And I'm going to go ahead and lie the blame squarely at the feet of ARP somewhere in the path. So if we hit the up arrow key and do that same ping again, because the ARP caches are all completed, we don't have any problem with that path. It's working great. If we are using inside of our organization's RFC 1918 private IP addresses, like the 10 network and so forth, we need to do network address translation at some point before those packets reach the public internet. And in this lab, I'd like to walk you through an example of how to configure exactly that. So let's start off with a plan regarding how we're going to implement network address translation. And we're going to use R3, and it happens to be a Cisco router that we'll be configuring network address translation on. I guess the first question we could address is who? What do you mean, Keith? Who? Who or which IP addresses do we want to translate? And if we just want to translate people coming from this 10 network, this 10.1 network, we could go ahead and identify that. So the people who get to be translated as they go out to the internet are people who have a source IP address coming from the 10.1.0 network. So that's the who that we'll train R3 to pay attention to. So whenever R3 sees packets from that source network, it'll say, okay, great, I need to translate this. As those packets go from the inside of the network to the outside, from a network address translation perspective. The next question that we probably ought to address is, what are we going to translate those IP addresses into? So let's imagine for this scenario that we've talked to our service provider and we have purchased a small quantity of addresses off of the 67.83.45.0/28 network. So let's go ahead and pick 4 addresses because real IP addresses on the internet aren't cheap. So we'll go ahead and use 67.83.45.11, and let's go all the way through 67.83.45.14. And that'll be more than enough addresses to support this little network, which at the moment only has a single PC in it at the moment. And the third question, I suppose, is where? So we'll implement this on R3. We'll also need to train R3 regarding which interfaces are part of the inside network here on the left and which interfaces are on the outside. And here are the commands that we're going to use to implement those instructions here on router 3. We're going to go into configuration mode, and we're going to first answer the question of who with an access control list. We're going to create access-list space 1, which is an example of a Cisco standard access list, and we're going to use permit 10.0.0.0 with a wildcard mask of 0.255.255.255. Effectively, for a wildcard mask, wherever there's ones regarding this wildcard mask, that means we don't care about those respective bits in the IP address. So the bottom line is that anybody who sends a packet where their source IP address begins with 10, that's going to be a trigger in the mind of R3 that that packet, as it goes through the router, needs to be translated to a routable address. The next entry is specifying the addresses that we're going to use for those translations. The syntax is IP NAT pool, the name of a pool. So in our example, we're naming this our pool in uppercase, and then we're specifying the first and last addresses in the range of that pool. So starting at .11, ending in .14, which are all addresses that live on this /28 network. We're also going to include the net mask of 28 bits. That's how we spell 28 bits in dotted decimal, as part of the creation of that pool of addresses. And this next entry takes part A and part B and marries them together. The syntax is IPNAT, which indicates we want to do network address translation for traffic on the inside, that's coming from the inside, in this example coming from PC1 going that way, if the source address matches list 1, which is access list 1, looking for any IP addresses that start, the source IP addresses that start with a 10 in that first octet. And if that's the case, we want to go ahead and do translation to our pool, which is this guy right there, which is the global address of 67.83.45.11 through .14. Now, PC1 doesn't need more than a single IP address for network address translation, but if he takes one up, we still have 3 more for other devices. And the last piece that we need to tell this router is which interfaces are connected to inside networks and which interfaces are connected to outside networks. In this example, we just have one going each direction. But we could have 3 or 4 interfaces connected to other inside networks as well. And the way we train a router that this interface, 1/0, is connected to an inside network is by going to that interface in interface configuration mode. In this example, interface gig 1/0, and using the command ipnat inside. That's the magic. And then we'd go to the other interface and use the command ipnat outside. That's gig 2/0. And then when we're done, any packets that are going through the router from the inside to the outside, if the source IP address has a 10 in that first octet, it's going to be translated into the pool that we just defined before that packet is forwarded out to the internet. So here on router 3, in order to make this not be just a typing exercise on my part, I've taken the liberty of putting those commands that we've just reviewed step by step into Notepad here temporarily. Just going to highlight those, right click and copy them, and then I'm going to right click in the terminal window here for R3, which will paste those commands in. So that should have implemented NAT on R3. So if we do a show ipnat translations, currently there's no translations because there's no traffic going through it, but we can change that. Let's go over to PC1. And here on PC1, let's do a trace out to 4444, and that'll send some UDP traffic. We'll go back to router 3, hit the up arrow, use the same command again, show IPNet translations, and now we have some translations based on the traffic that's going through R3. So here's PC1's inside IP address of 10.1.0.11, as well as some port information that it chose to use for source ports. And when those packets were forwarded out the outside interface of R3, they got translated to the IP address of 67.83.45.11, which is the first IP address in our pool, with the same source port. And because it's NAT and not PAT, that same IP address that PC1 is using won't be used by other devices and their translations at the same time PC1 is using it. So what I invite you to do is get some hands-on practice using the labs we've provided and have some fun both implementing and verifying network address translation on a Cisco router.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.